Part 3, the principle of least action. So we are going to discuss the principle of least action. We're going to do the math for a simple Newtonian system. And you can see my video on energy to see exactly what I mean by that. But what this theory is really about is it's a theory in the purest sense, okay? So it asks about what actually happens in nature and what theoretically could happen in nature. So this is why I say it's a theory in the purest sense. In the little diagram on the left here, I've got x on the vertical axis and time on the horizontal axis. So this could be, maybe y would be more appropriate, but it's just a position, okay? So imagine you threw a ball up in the air and it came back down. This would just be how that ball varies with height, for example, over time. And what I'm saying is that x bar is the actual path that nature takes, or nature imposes on the system. And x, which I'll put in white here, I'm going to call a theoretical path. In everything that I've described so far, it doesn't appear that there's anything limiting x from happening, okay? There's nothing, we don't think that there's anything that constricts this. So what you might say is that the theoretical path, x, okay, is going to be equal to the actual path, put it in red, x bar, plus some error term. There's a difference between these two, and we're going to call the error term eta. Similarly, if you take the time derivative of x, so if you take dx by dt, you get d by dt on x bar plus eta. Now, we're going to use dot notation, so I'm just going to simply say that x dot is equal to x bar dot plus eta dot. Okay, so we've got a couple relationships between speed and position for this theoretical versus actual path. We are going to use something called calculus of variations. Okay, that's what's needed for this problem. So what I want to do next is I want to calculate the kinetic energy of this theoretical flight path. So I told you in the last video that the kinetic energy EK is equal to 1/2 mv squared, which is, in this case, v is the theoretical v. So this is going to be 1/2 m times x bar dot plus eta dot all squared. All right, doing the math on this, we get 1/2 m x bar dot squared, first term squared, plus 2 of x bar dot n dot, and then we get plus n dot squared. So what I'm going to define here is that if you take, and this is a statement or a definition or a postulate, I'm going to say that if you take dn by dt squared, I'm going to say that that equals 0. So if you take the time derivative of the error and you square it, it's effectively 0. You might say it goes to 0. What I'm saying is that the error is so small that if you squared it, if you take the error with respect to time and you square it, it's essentially 0. Okay, and this is one of the conditions of this derivation. So with that, we know that this is gone. We know that that's gone. And then what we're left with is 1/2 m x bar dot squared plus m, see if I can get it in here, x bar dot plus, times eta dot. Of course, the 2 and the half cancel there. Okay, so we have this expression for kinetic energy. Now you might ask, what about potential energy? Scrolling down a bit, what about potential energy? I said in the last video we don't know anything about potential energy, and it's true, we don't really. But if you have potential energy E, it's called EP, and I'm asking what is the potential energy of this theoretical flight path? Well, I might say, what is this near x equals x bar? So what I'm saying is, how can we estimate or approximate this function near x bar? So we can do a Taylor series expansion. We're going to do a Taylor series expansion. And it is a true Taylor series because we're not doing it around near zero, which I've done in some previous videos. So what we get is that near x bar, it's going to be approximately equal to, maybe I can say approximately here, but we will be equating it. Approximately equal to EP at x bar plus EP prime or EP dot at x bar, and then times x minus x bar. Well, recall our definition of x. X, which is literally, it's actually right here. We can still see it. X minus x bar is actually equal to eta. Okay, so that's kind of nice. So now we're saying approximately, if you take x being near that actual path, flight path x bar, we're going to get it's equal to EP x bar plus EP prime, which is really, let's write it out explicitly. What do I mean by EP prime? I mean the derivative of EP with respect to x evaluated at x bar times, and x minus x bar is eta. Okay, so that's sort of kind of interesting. We established EK, so we've established, let's call this 1 and 2, EK and EP. Well, let's get back to our principle of least action. The principle of least action states that S is going to be equal to the integration from T1 to T2 on the kinetic energy minus the potential energy, dt. And in the calculus of variations, what you assume is you have the S in this case is going to follow X. It's going to have a bar quantity, and then it's going to have an error quantity, which we can call delta, lowercase delta S. Okay, so we're saying that it's going to be equal to actual S, which is the principle of least action calculated for the actual S. What we observe, you might say this is the observed phenomena plus an error term, Remember what we're doing here. We're calculating the principle of least action for a theoretical path S. This is theoretical. All right, well, let's plug in some of our numbers here. And I'm going to rewrite what we got for EK. Just bring it down here. Okay. So we got EP. We've got EK. Let's fill that in. So we get S is equal to the integration T1, T2. EK is half M x bar dot squared plus M x bar dot N dot, okay, the time derivative of N. And then minus, you're going to have EP at x bar minus, and let's go back to the prime notation. We're going to call it EP prime at x bar times N. And of course dt. All right, so if we do a little bit of rearranging here, we're going to notice something. If we split this up into two integrals and we bring together sort of like terms, if you will, we're going to get half mx bar dot squared and then minus EP at x bar. That's one term. And then the other term is, let's use orange. It's going to be minus, so to do a subtraction here, the integral t1 to t2. And what you're left with is mx bar dot n dot plus ep time with the derivative respective position, the theoretical position, evaluated at x bar times eta dt. And what we're going to say is that this part is equal to s bar, which should be obvious from the definition of the principle of least action. Actually, let's do blue, make it match. So I'm saying this is equal to s bar, and I'm saying this is equal to that delta s. Okay, we're going to continue this next time and do some more of the math on this one.